Chapter 3, Working with Units. In this first screencast, we explore some basic ideas associated with units of measurement. Measurements arising in everyday life are given in terms of specified units. For example, the height of a door is 7 feet. Feet are the units. The fuel efficiency of a car is 26 miles per gallon. The units are miles per gallon. The power rating of a clothes dryer is 1,000 kilowatts. The unit of measurement is kilowatts. The area of a tract of land is 15 square miles. The unit of measurement is square miles. The per capita birth rate is 1.1 births per female per year. The unit of measurement is births per female per year. The energy generated by a wind turbine over a month is 5.6 megawatt hours. The unit of measurement is megawatt hours. In some cases, the units are fairly basic, like feet. In other cases, the units are more complex, made up of combinations of basic units. For example, the units births per female per year, this is a complex unit, and it's made up of 3 separate units, namely births, females, and years. Sometimes there are prefixes, like kilo or mega, preceding the units. And sometimes words like per are used. So in this first screencast, we will discuss complex units such as these. Let's start by talking about prefixes. For large and small measurements given in metric or standard international units, prefixes are commonly used to express values more simply. For example, the prefix kilo, which is abbreviated with a K, means to multiply by a factor of 10 cubed, or 1,000. For example, let's take 25,000 meters. That's a fairly large measurement. We know from Chapter 1 that we can write 25,000 as 25 times 10 cubed meters. So instead of multiplying by 10 cubed, we can replace this factor of 10 cubed with the prefix kilo. So instead of saying 25 times 10 cubed meters, we would say 25 kilometers. We frequently express units in abbreviated form. Since meters is abbreviated with M and kilo is abbreviated with K, we would abbreviate kilometers with km. So, in abbreviated form, we would say that we're expressing 25 times 10 cubed meters as 25 kilometers. The table below shows other common prefixes, the powers of 10 that they represent, as well as their abbreviations. For example, let's take the prefix nano. The prefix nano means to multiply by a factor of 10 to the negative 9. You'll recall from Chapter 1 that taking 10 and raising it to a power of negative 9 means that you're really taking 1 over 10 to the 9th power. 10 to the 9th power is a billion, so this is 1 over a billion, which is the same as a billionth. So when we use the prefix nano, really what we're doing is multiplying by a factor of a billionth. The abbreviation for nano is N, So if you see a letter N in front of some other metric units, you would know that the unit has the prefix nano in front of it. Similarly, we have the prefixes micro, milli, centi, hecto, kilo, mega, giga, and tera, and each of these prefixes again represents a factor of 10, and you can see as we go through the table the factors of 10 grow. So these prefixes here represent very large factors of 10, whereas these prefixes represent very small factors of 10. So let's try out our understanding of these prefixes in example 3.1. Express the given measurements in the specified form. Let's start with part A. Express 1 centimeter in units of meters. Okay, so we have to start by interpreting the prefix centi. If we look at our table above, centi means to multiply by a factor of 10 to the negative 2. So instead of writing centi, I can write 1 times 10 to the negative 2 meters. 10 to the negative 2 is a hundredth, so this is 0.01 meters. Now let's look at part B. Express 1 milliliter in units of liters. So again, we need to start by just looking at what the prefix is. In this case, the prefix is milli. If we look up above at our table, we see that milli represents multiplying by a factor of 10 to the negative 3, which is really the same as a thousandth. So, if we go back down here, instead of writing 1 milliliter, we can instead multiply by a factor of 10 to the negative 3 liters. And as we said, 10 to the negative 3 is a thousandth, so this would be 0.001 liters. Now let's look at part C. Express 1 kilocalorie in units of calories. So again, we start by looking at the prefix. In this case, the prefix is kilo. We've seen kilo before. Kilo represents multiplying by a factor of 1,000 or 10 cubed. So instead of writing 1 kilocalorie, we can say we're going to multiply by 10 cubed calories. So this would be 1,000 calories. Let's look at part D. Express 1 gigabyte in units of bytes. So let's start by looking at the prefix. The prefix here is giga. If we look at our table above, we see that giga represents a factor of 10 to the 9, which is a billion. So here, instead of writing giga, we would write 1 times 10 to the 9th bytes, which is the same thing as 1 billion bytes. Let's look at part E. Express 1 megawatt hour in terms of watt hours. So again, we start by looking at the prefix. In this case, it's mega. The prefix mega represents multiplication by a factor of 1,000,000, or 10 to the 6. So we could rewrite this as 1 times 10 to the 6 watt hours. Or in other words, 1,000,000 watt hours. Okay, now let's talk about something a little different. Multiplying and dividing units. Calculations that we perform frequently require us to multiply or divide measurements that have units. To determine the units of our final answer, we similarly multiply or divide the units. The next 3 examples will illustrate this point. So let's start by looking at example 3.2. The energy required to run an appliance is calculated by multiplying the appliance's power, which is usually given in units of watts. We multiply the power by the hours that the appliance is run. Suppose that a coffee maker is run for 10 minutes. The power ratings of coffee makers range from 900 to 1,200 watts. Let's assume that our coffee maker has a power rating somewhere in the middle. We'll say 1,050 watts. So let's go ahead and calculate the energy required to run the coffee maker. Okay. So, to calculate energy, we take the power of the appliance and we multiply by the hours that the appliance is run. Now, for the coffee maker, its power rating is 1,050 watts. We need to multiply that by how many hours we've run the coffee maker. Now in this case, we've run the coffee maker for 10 minutes. We need to express the 10 minutes in terms of hours. 10 minutes is 1/6 of an hour. So I'm going to go ahead and write 1/6 of an hour. So we need to multiply these two numbers, 1,050 by 1/6. Multiplying by 1/6 is the very same thing as dividing by 6. So if you take 1,050 and divide it by 6, you ultimately arrive at 175. So the energy is 175 watt. What should the units be? Well, We multiplied watts, a certain number of watts, by a certain number of hours. Just like we multiplied the numbers together, we multiply the units together. And so our answer will have units given by the product of these two units. So the units here are watt hours. And you can see the dot right in the middle indicates that you're multiplying a certain number of watts by a certain number of hours. So the energy that we have used in running this coffee maker is 175 watt hours. Let's go ahead and look at the next example. The area of a circular region is given by the equation A equals pi times r squared, where pi represents the Greek number 3.14159 with additional digits, and r represents the radius of the circular region. Let's go ahead and find the area of the circular region that has a radius of 70 meters. Okay, well, if the area of a circle is given by the equation A equals pi times the radius squared, and we want to find the area when the radius is 70 meters, then we need to replace the r, the radius, with 70. So we will have pi times our 70 meters squared. Okay, we're going to need to work out the numerical calculation here. We will end up taking pi and multiplying it by 70 squared. If you take pi and you multiply it by 70 squared, you arrive, I'm going to use squiggly lines here to indicate that we're going to get an approximate answer here. We're going to get an approximate answer of 15,394. Now the real question here is, what are the units? This is the area. We've calculated the area, but it's 15,394 what? Well, let's go back and see where the units appeared in the calculation. We were squaring 70 meters. Not only is the 70 being squared, so is the meters. We're squaring the meters. In other words, we're taking meters times meters. So our units in our resulting answer are going to be meters times meters, or in other words, meters squared. So this would be square meters, or meters squared. Okay, let's go ahead and look at our next example. Let's suppose a person has driven 1,400 miles over the course of 4 days. So how many miles on average did the person drive each day? Well, this would be a division problem. If you want to take the 1,400 miles and split it evenly over the course of 4 days, that would require a division. So we would take 1,400 miles and divide this over 4 days. Now, we can also write this as 1,400 miles over 4 days. This is two different ways of expressing the same division. So if we have to take this 1,400 and divide it by 4, we will arrive at 350. So how many miles on average did the person drive each day? Well, the answer is 350. But what are the units? Well, how did we arrive at the 350? To arrive at the 350, we ended up taking a certain number of miles and dividing by a certain number of days. The units of our answer will result from dividing the miles by the days. And so our units are miles divided by day. So we would read this. We would read our answer verbally by saying 350 miles each day. Now let's talk about the word per. The word per means for each. So an equivalent way of writing our answer above might have been to say 350 miles per day, instead of saying 350 miles each day. Quantities that have divided units, like our example above, or use the word per in their units, can always be expressed as fractions. Here are a couple of examples. If we have 350 miles per day, which again is the same thing as what we have written here, we can write this in fractional form as 350 miles divided by 1 day. So this representation is equivalent to this representation is equivalent to this representation. They all mean the same thing. In this example, 0.04 tons per acre, again, that's how you could verbally say this. This can be expressed in fractional form as 0.004 tons divided by 1 acre. Let's go ahead and look at example 3.5. In this example, all of the quantities in parts A, B, C, and D have units that are either fractional or involve the word per. Let's go ahead and express each of these quantities in fractional form, just as we saw. Let's go ahead and look at part A. 365 days in a year. That's how we could say this. We could also say 365 days per year. So if we want to express this quantity in fractional form, we would say 365 days divided by 1 year. Let's go ahead and look at part B. 1,000 meters per kilometer. Let's go ahead and write that in fractional form. I would say 1,000 meters, and I'm going to write the abbreviated form this time, divided by 1 kilometer. Remember, kilo is abbreviated K, meter is abbreviated with an M. So that would be the fractional form. Now let's look at part C. 7 cents per kilowatt hour. So some of these abbreviations here may be a bit new. The K is an abbreviation for kilo, the W is an abbreviation for watt, and the H is an abbreviation for hours. So this is read kilowatt hours. So the whole thing is 7 cents per kilowatt hour. If we write this in fraction form, it would be 7 cents divided by 1 kilowatt hour. Okay, let's have a look at part D. 2,400 calories per person per day. Again, every time you see the fraction bar, you can read it as the word per, or you can read it as the expression for each. So we could also say 2,400 calories for each person for each day. Now, let's go ahead and figure out how we would express this as a fraction. There are really two divisions to perform here. You can see there's one division here and one division here. Generally, we do divisions left to right, so we perform this division first and this division second. So this is what it would look like. We take 2,400 calories, and I'm going to abbreviate this CAL, divided by one person. So you can see here, I'm doing the first division here, and this would be my result. Then I'm going to divide by 1 day. So I'm taking the whole quantity and dividing it by 1 day. Now, if you recall from chapter 1, a fraction like this is called a complex fraction because you have a fraction within a larger fraction. And there are ways of simplifying complex fractions. So we're going to go ahead and do that here. Okay, 2,400 calories divided by one person. Now, we're dividing by 1 day. I'm going to go ahead and rewrite it this way. This is just a different way of expressing the same division. The reason I'm writing it this way is because I want to take the next step, which is the following. Dividing by 1 day is the same thing as multiplying by the reciprocal of 1 day. And it's a little easier to see that if we use this form of the division. So I write 2,400 calories over one person times the reciprocal of 1 day, which is 1 over 1 day. So now we have two fractions to multiply. If you recall from chapter 1, we multiply fractions by multiplying their numerators and multiplying their denominators. So when we do that here, when we multiply the numerators, we arrive at 2,400 calories again. When we multiply the denominators, we take the 1 times the 1, we get 1, and then we take the person times the day, and we get person times day, of course. So our denominator ends up with 1 person times day. Okay, so This would be the simplified form of this complex fraction. Whenever it is beneficial to write a fraction like this that involves two divisions, or equivalently, the word per is used twice, the fraction will always have a simplified form like this. Notice that every unit that occurs after the division or after the word per will be found in the denominator of the fraction. Keep that in mind as we go forward. So let's look at the next example here. "179 bushels per acre per year." So this example is just like our last example. We have two divisions that have to occur, or two words that follow the word per, and we need to express this in fraction form. We'll do it in exactly the same way that we did it in our last example, but this time we're not going to run through all of the math that we did up here. We're going to go directly from our initial expression down to our final expression using what we learned from the previous example. So we start with 179 bushels. Okay. Now if we look at our expression, it's per acre per year. Now recall, units that occur after the word per occur in the denominator. So this will be dividing by 1 acre times year. Okay, let's have a look at our next example. Each of the following letters represents a variable quantity. Express each variable as a fraction. So this example is actually very similar to the last example. Our goal is identical. We want to express each of these quantities as fractions. The only difference is, in our last example, you were given numerical quantities. Here you're given variable quantities. But remember, every one of these variable quantities represents a number, just like it would have in the last example. So let's have a look at part A. We have E miles per gallon. You have to think that E represents a certain number of miles. Maybe E is 20, so we might be saying 20 miles per gallon. But instead, it's E. How do we write this as a fraction? Well, we do it the same way we did it in the last example. We write E miles divided by 1 gallon. Now let's look at part B. We have R riders per bus per day. So this is another example of a situation where you have two divisions going on in the units. So we've seen what to do in situations like this. So we start off by writing R riders divided by 1 bus times day. So this would be the fractional form for this quantity right here.